Okay. Okay, so far, we've got this band model, and it gives you something that is, we said, sort of a cartoon or caricature of a direct gap material. You're going to have one valence band and one conduction band, and they're going to be mirror images of each other, identical except one is turned upside down from the other, because it was like Eg over 2 plus or minus the square root of this delta squared plus sine squared term. So the plus gives you the conduction band, the minus gives you the valence band, and they're identical in every way except one is going up and one is going down. Right? So now the question is, if you wanted to, really kind of use this as a simple model for a specific material, how would you do that to get, well, there's two things you would want. You would want to fit the effective mass, and you would want to fit the band gap. And we already know how to get the band gap, right? Eg was just equal to EC minus EA. Those are your two site energies. Right? So you choose the difference in your site energies to give you the band gap, and you don't. And often when you're doing these empirical models, you choose your valence band edge, which would be EA, to be equal to 0. So if this is your valence band edge, often in empirical models, you just set that equal to 0. And so then EC is basically your band gap. Well, that's easy. And now what about T? How do you choose T? And so, well, T is chosen, that was the other parameter. T is chosen to fit the effective mass at gamma, to give you the right m star, or effective mass, at the gamma point, which is k equal to 0, and which is your band edge. Right, so here's my k equal to 0 point. So you want to get the right effective mass at your band edge. And because these bands are completely symmetric, the electron mass will be identical to the hole mass. And so this is where depending on what you're trying to do, you choose the mass that's most important to you, because you only get one out of this model. You can't get two different ones. Okay. And often you'll see that, and this really is, so this band physically corresponds to the light hole band. We'll see there'll be three bands: light hole, heavy hole, and split off. This would correspond to the light hole band, and well, the one above it is the conduction band, obviously. There's no problem. There's only one conduction band. And we'll see the light hole band, the effective mass of the light hole band tends to be, pretty similar to the electron band. So it's not too bad from that point of view. Okay, so you choose your favorite mass, whether it's a conduction or light hole, whichever is more important to your problem, and you choose T so that you get that mass, or maybe you want the average of the two, whatever. You can choose T to get the mass you want. So how do you do that? Well, the effective mass is always given by the same formula, 1 over m star. Is 1 over h bar squared d squared e dk squared. So you just have to take this dispersion relationship and take the second derivative, evaluate it at k equal to 0, and see what you get. So I won't go through all the details, but just a starting point is you write down the dispersion relationship. So E is Eg over 2, and since we're looking, let's say I want to choose the conduction band mass, because if I take the second derivative, that'll be positive instead of negative, because it's just a curvature. So Eg over 2 quantity squared plus 4t squared. So that's our starting point, and then we take the second derivative. And so without going through all the gory, nasty details, what you end up with is 1 over m star is equal to, and I guess this has to be evaluated somewhere, so this is evaluated at k equal to 0. So I take the second derivative, I evaluate it at k equal to 0, and this is what I get, divided by h bar squared. And so that relates my m star, which is what I know, because I know what material I'm trying to model. And I know the band gap, and I know the lattice constant. And so therefore I choose my t to get the mass that I want. All right. So this gives me my t. So what have I got now? So in this two-band model, t squared is equal to h bar squared times the band gap divided by 2a squared effective mass. And that's how I would go about choosing this magnitude of this off-diagonal coupling element in this two-band model to give me the right effective mass at the band edges. And so that's our two-band model. For our single-band model, where we just had one atom per unit cell, one S state per atom, we had T, and you just get one band, one cosine band. This was the relationship between that hopping element T and the effective mass and the lattice constant. So what enters into the two-band model is the band gap. And in fact, off-diagonal matrix element in the two-band model is just the geometric mean of the one you had in the one-band model times the band gap. I've never seen anyone write it down like that, and I'm not sure if it has too much physical significance, but all I see immediately when I write it like that is that that matrix element is increasing as the square root of the band gap. I'm not sure how to interpret that. But at any rate, those are so we've had two simple models so far. Our single band model where we get one cosine band. This two-band model where we get two bands, a conduction and valence band. And this is how you would choose the off-diagonal hopping elements to give you the right effective mass. Okay, so let's just say a few things about this two-band model that we have. Actually, we have three band models so far. The parabolic, the single band model, and our two-band model. And if you were to draw them sort of all in the same graph, well, only one of them has a valence band, so that makes life easy, right? Only our two-band model has a valence band. All the others only have a single band. So this would be the valence band from our two-band model. And of course, the conduction band is identical, just flipped upside, right, flipped the other way. So this would be the conduction band from our two-band model, which is supposed to look symmetric. And then we would have our conduction band from our single band model, which is a cosine band, which would look something like this. I guess I didn't talk about the band width. And lastly, we would have our parabolic model, which is just a parabola that just has no repeat, it's not periodic, just a parabola like that. Your effective mass model, and it just goes as h bar squared k squared over 2m star. And then this is our single band tight binding model, and that just goes as h bar squared over m star a squared, h bar squared over m star a squared times 1 minus cosine ka. And finally, our two-band model, Eg over 2 plus minus square root of all that squared plus that sine 4t squared sine squared Ka over 2. And all of them, right, at k equal to 0, all of them have the same m star at k equal to 0. That's the way they're all constructed. So at k equal to 0, they all have the same effective mass. And right at the band edge, they all have the same density of states. And it's only as you go to energies above the band edge that things start to become different. And people talk about non-parabolicity. So the two-band, I don't know, the two-band model is more non-parabolic than the single-band tight binding model, which is more parabolic than the parabolic model, which is completely parabolic. I mentioned the density of states, so let's see. Okay, yeah, okay. Well, first let's talk about what people call non-parabolicity. And we'll derive something that's used very commonly in the literature from our two-band model called a non-parabolicity parameter. And it's sort of a cheap way to take into account the fact that the bands are really non-parabolic without having keeping things as simple as possible. Parameter that defines how non-parabolic your model is. Let's see. So we're going to start with our dispersion relationship, and I'm going to call my E as epsilon of k now because I'm going to change variables at some point. So epsilon of k is our Eg over 2, and I guess I'm just going to look at the conduction band. All right, forget the valence band. Let's just look at the conduction band. Plus Eg over 2 squared plus 4t squared sine squared Ka over 2. And we are interested in the density of states near the band edge. So D of E is the density of states. And so mathematically that means that near the band edge, right, because the band edge occurs when k is 0. So this just means we're interested in small k near k equals 0. And if Ka is much less than 1, then we can just replace that sign with, like sine theta is theta for small theta. All right, sine theta is theta for small theta, so that's what we're going to do. And let me just rewrite that. So then we have E of k, and then that sine term just becomes plus 4t squared k squared a squared over 4. Right, just replacing sine of theta with theta. So sine squared theta becomes theta squared. And, well, the 4's cancel out. And now I move this term to the other side. I move this term over here, and I square both sides. And so I get epsilon minus Eg over 2 quantity squared is just this stuff. Eg over 2 squared t squared plus this term. And now what I'm going to do is use the relationship between T and the effective mass that we just derived to replace T by this. So I'm going to replace T by this. So I actually have a T squared. So I'm going to replace T squared by this at this point. All right. And so so then this term, second, I'm replacing the T squared by that, what I just showed you. So then I have h bar squared, band gap, and the a squares cancel out. And then I just do the squares. I have e squared minus epsilon times the band gap plus this last term squared, which is going to occur on both sides, so I can cancel it. Eg over 2 quantity squared is Eg over 2 quantity squared plus this last term. And this last term I'm writing now is something that looks kind of familiar. H bar squared, k squared over 2m star times the band gap. And so these two terms cancel. And then I just divide through by the band gap, okay? And so the final equation I get, dividing through by the band gap, is that the way we wrote our dispersion was that the zero of energy, epsilon equal 0, corresponds to the valence band edge. That's the way we wrote that dispersion a little bit initially. And now I'm only interested in the conduction band, so I would like epsilon equals 0 to correspond to the conduction band edge, so I don't have to carry around some extra constant. So I want, right now we have this situation, 0 and Eg for the conduction band edge and the valence band edge. And I would like I want my conduction band edge to be at E equals 0. Since we're only interested, we only care about epsilon greater than or equal to the band gap. Right, we're only interested in these energies here in the conduction band, because initially this is the dispersion for the conduction band, not the valence band. So we're looking at the conduction band. So I need to shift my energy 0. So I'll define a new variable. This is why I called it epsilon initially. My new variable is E, which is epsilon minus the band gap. Right? So when epsilon is the band gap, that is in 0, or in terms of this new variable, epsilon is equal to E plus the band gap. And so wherever I see an epsilon, I substitute, this into here, and I just work it out, and I finally get, and if we didn't have this term here, it would just be your normal parabolic dispersion. And this is why this is called your non-parabolicity parameter, which I'll generalize in a moment. But you can immediately say, or you can think of this as your correction term, right? If this term were 0, you would just have a parabolic dispersion. And, well, obviously, the smaller the band gap, the larger this correction is. Right? The smaller the band gap, the bigger this correction is going to be. It's inversely proportional to 1 over the band gap. So for a band gap like for indium arsenide, for example, which is a narrow band gap semiconductor, that's like 0.3 eV. So you're 1 over the band gap. It's like 3 1/3. And this gives you an idea, how large your energy is before this term starts to become important. So as your energy starts to increase to some fraction of the band gap, then this thing starts to look more and more parabolic. You start diverging from your parabolic dispersion. And in the textbooks, you're going to see this expression generalized invariably to the following form. And this is your non-parabolicity parameter, this alpha. And you can find this, in a lot of references, values given for different materials. So this alpha is chosen to give the best fit to the EK relationship, within some small energy range around the band edge. And that energy range is just going to be determined by the particular problem you're interested in, whatever gives the best fit over some energy range near the band edge. And that can be determined by the doping, basically how high up in energy you need to worry about an applied voltage, something will determine the energy range of interest. Okay, so one place this model is used for is to get a reasonable approximation to the density of states. So this affects the density of states. If your dispersion is flatter, your density of states is bigger, which means you can fit more electrons into a smaller energy space. And that affects where your Fermi level is, which is sort of a crucial parameter in device modeling. You need to know where your Fermi level is, and to know where your what you do know usually is your doping. The guy who grew the material tells you what the doping is, and then you need to know where the Fermi level, figure out where the Fermi level lies. And you do that by integrating the density of states weighted by the Fermi factor. So let's keep this final expression in mind. Let's take a look at what we mean by the density of states, and then derive the density of states using this dispersion relationship, and see how it differs from your normal one that you find in the textbooks for a parabolic dispersion. Okay, so we're going to calculate the density of states using this dispersion relationship. Okay, so density of states. There's probably easier ways of doing this, but it's useful. This is sort of a more advanced expression people write down that at first looks really weird, but I will write it down. So here's one definition of the density of states, and then we will directly calculate it from this. So in 3D, our density of states is 1 over the volume, sum over k, Dirac delta function of E minus this epsilon of k. And this is why we already talked about converting sums to integral. Because when you see it in a sum, it looks really weird. But once you see it inside an integral, it's a little less unnerving. Because that's what we do with delta functions, we integrate them. So V is the volume of your sample, just a normalization, which will go away. But if you look at this, I mean, right away, you see it has the right units for density of states. It'll have the units of 1 over volume, right? And what are the units of the delta function? Well, what are the units of the argument of the delta function? What are the units of the argument of the delta function? Energy. So what are the units of the delta function? Okay, so if the units of the argument are energy, what are the units of the delta function itself?
1 over energy.
Yeah, 1 over the arguments of the delta function. I mean, yeah, the unit of the delta function is always 1 over the unit of the argument. Because when I integrate, if I just have delta, if I have like integral dE delta E, by definition, this is just equal to 1 with no units at all. So the delta function, right, dE has units of energy, so the delta function better have units of 1 over energy. That come out to something, and that's in fact what it is. So just for your future reference, if you didn't know it, the units of a delta function are 1 over the units of its argument. Okay, so this is our definition of the density of states. I guess if we want to be really fastidious, this is for 1 spin, which since we're not even worried about spin. And if you want for both spins, you multiply by 2 at the end. All right. And so, what we did when we talked about our periodic boundary conditions on how to convert a sum into an integral, then, well, you do this right away. So the density of states is equal to integral d cubed k. Okay, and then, well, we know what our epsilon of k is. Our epsilon of k is, in this case, this would be my E is that's my function, my epsilon of k, and this is the same E here. It's an implicit function of k because I got E and E squared on the left-hand side, but that is my epsilon of k. That's what we mean by our epsilon of k. So it's kind of confusing because here E is, anyway. But the important point is that this epsilon of k here does not depend on the angle. It's only a function of the magnitude of k. That's the point I want to make. It's only a function of the, so this is only a function of the magnitude of k, therefore I can integrate over the angle analytically, right? That solid angle. And so I integrate over the angle and I get 4 pi, right? So taking all that stuff out front. So this is due to the integration over the solid angle, 4 pi over 2 pi quantity cubed, times the integral. Okay, so this is just now an integral over the magnitude of k. And this epsilon to k is just a function of k. And this is, usually I have to end up rederiving this for everyone because they've forgotten how to do this. So this is out front, we have a 1 over 2 pi squared integral dk k squared. And this thing becomes delta k minus k0 over the magnitude of the derivative of my function with respect to k and evaluated at k0. So I'll just put a k0 in there. And probably most of you have completely forgotten that attribute of delta functions. How to integrate a delta function of a function. So I'm looking at generically a delta function of a function and wondering how to integrate that. I mean, this is what we're looking at generically. How to integrate, because my epsilon k is a function, right? Some function of k. And I want to know if I'm looking at something like that. I don't know if does that look familiar to anyone? So, this delta function is only going to give you something when the argument is 0, right? It only gives you something, so you look for zeros of that argument. And so when is that argument going to be 0? Well, I'm going to say that this argument is 0 whenever k equals k0. I don't know what that is yet, but just let me write it down. So I'm going to, f of k0, for some k, I'll call it k0, equals 0, right? And so near k0, f of k equals f of k0, which is 0 by definition, right? Shoot. F of k, I'm going to do like a Taylor series expansion, plus df dk evaluated to k0 times k minus k0. So near this k0, I can write my function like this for k very close to k0, and by definition, this is 0, right? Because k0 is when my function is 0. So I'm expanding around the 0 of the function. And so since my delta function only gives me something when k is very infinitesimally close to k0, I can just replace the argument by this thing here. And so then I just replace the argument with that, and I have integral dk delta, this df dk evaluated at k0 times k minus k0. But this thing here is just a number, right? This is no longer a function. That's just a number. It's just a derivative evaluated at a certain k. So now I use this other property of the delta functions, that delta ax is equal to delta x, hopefully this rings a bell, over a. I don't want to have to prove this one. Okay, I'm just going to use this one. And so my a, this is my a. This thing I circled is my a. And here's this thing down here is my a. That's my df/dk down there. Okay? That is my df/dk. Now, I mean, if, for some E, this is always, I just choose E so that, for some E, that's always going to be 0. Or given E, given some E that's within, we're talking about this, we're just integrating over our conduction band. We have our epsilon of K that looks like this. So for any E in that range, right, that I'm going to get a 0. For any E in this range, that argument will be 0 for some K, right? So every K, I'm always going to get something. And so finally, I just do this integral. I just now can evaluate this analytically and then just plug in my dispersion relationship, which is what I'm going to do. So I can get an analytic form for my density of states. And so this is just equal to, whenever you have a delta function in the integral, it makes life really easy. So that's just 1 over 2 pi quantity squared. You just evaluate all the arguments at k0 times k0 squared over. And now what we got to do is evaluate the derivative of that dispersion relationship. And, we can use this. So that's the expression. And now let's evaluate what we need and get the density of states, right? So this is my density of states. And I'm going to have to then, what we're going to have to do is map this K0 back to E, which is what we're going to do. Okay, so what do we need? We need a derivative, and we need K as a function of E. So let's go back and look at our dispersion. We have E plus alpha E squared is h bar squared k squared over 2m star. That was our dispersion relationship. And so I just do implicit differentiation dE times 1 plus 2 alpha E is equal to h bar squared k over m star dk. And so dE dk is h bar squared k over m star times 1 over, that's my dE dk, and the only other thing I need is k as a function of E. So just taking the square root of both sides of my dispersion relationship here, I get that k is, so those are the two things I need. This becomes my K0. Here's my derivative, and I'm just going to plug that back, these two terms back into my formula for my density of states. I got my derivative, I got my K0, I just plug them in up there, and finally I get that the density of states after a little manipulation, so the density of states in our two-band model, or at least sort of the low energy form of our two-band model near the band edge, 1 over 2 pi squared m star. So there's the density of states in our that comes out of this when you have this non-parabolicity parameter in your close parentheses. This is the density of states you got from E. So that's the density of states that results from that. If you set the alpha to 0, you get the density of states that you normally get in your textbooks from your parabolic model. If you set alpha to 0. I guess remember, where alpha comes from and how alpha scales. So alpha is like 1 over the band gap. So if I look over here at my density of states term, I have this thing in the square. Here's the energy dependence of this in a square root. And then I have another energy dependence out here that's outside the square root. And I mean, if you have like a square root, and I guess in the parabolic model, I would just have what, m star 1 over 2 pi. So for parabolic, okay, so what you see is that as E starts to become comparable to alpha, right? Or alpha E. So for alpha E, greater than 1, then this thing the two models start to diverge significantly. Right? The two models start to diverge significantly. And, as alpha E becomes greater than 1, the energy dependence is going to be, the energy dependence of this guy will actually end up looking, for large E like E squared. Right? The energy dependence of that for large E will start increasing as E squared, where this is always just, this always just goes as square root of E. So usually people plot the density of states like this. So you have energy. This would be my band edge at 0. Here's your density of states. So the normal one just goes as square root of E. And the square root of E doesn't grow very fast. It just kind of is rather flat. But the other one, it'll start off like square root of E. And then it'll go through a period where it starts going linear, and then it will actually start at some point increasing faster than linear. So this would be like our two-band, our non-parabolic model. And the diversion starts happening as E becomes comparable to 1 over alpha, which is your bandgap. And so as I said, usually the doping. The doping is given by the experimentalist. And, in a simple model, you say the doping is equal to the, say, electron density. And the electron density would then be given by an expression like this, where you integrate the density of states times the Fermi factor, which is this exponentially decaying factor as energy increases. And your job, you do this integral, and your job is to find this Fermi factor. Doing this integral, you need to get the Fermi energy here. So you know this. You know your density of states. You don't know the Fermi energy. So from that expression, you can figure out the Fermi energy. And the problem is that if you're using the parabolic model for high doping, because the states in your parabolic model, they don't increase that fast. They stay down here. You'll end up with, if your doping is really high, you're going to have to get your Fermi level way out here to get all the electrons in there that you need. Whereas if you have this other non-parabolic density of states, because it starts increasing much more rapidly, you'll get the same area under the curve for a much lower Fermi level. That can make a big difference, a huge difference in something like indium arsenide, which is narrow bandgap. So for indium arsenide, and we ran into, we found this out the hard way. And I can't remember, if you dope it, say, like 10 to the 19th, and you use a parabolic model, for parabolic model, you get a Fermi level of about 1 eV above the conduction band edge, which is ridiculous. Fermi levels are never that high. They're always maybe a couple hundred milli-electron volt, maybe 400 milli-electron volt at most. You never have a Fermi level that high. And even in silicon, this same model works for silicon. People use it in silicon. We derive this for a direct bandgap material, right? But you can just kind of forget about where the derivation comes from and just use it. Silicon is an indirect gap material. People use it for the conduction band of silicon. You can find parameters for alpha. I don't think I wrote them down here. And you need to worry about this in silicon when the doping is, greater than or about equal to 10 to the 20th. So when the doping becomes greater than that, you have to, if you don't make a correction to your usual parabolic model, your Fermi level starts to be somewhat off. So, we derive this very specifically, but you can just use this in general, and silicon is the example. Just use this dispersion, even though it's an indirect gap material, and all the electrons are sitting out at X. You all know what the conduction and what the bands of silicon look like? So in silicon, in all of these materials, the valence bands all look pretty much the same. So the valence bands are all down here at K equals 0. You got your light hole, your heavy hole, and your split off. But in silicon, here's my pi over A, and I'll only draw half of it since you've got your minimum real close to the band edge out here, something like this. And so your conduction band edge is way over here, actually at about 0.85 of the way out to the edge of the zone. That's where your conduction band lives in silicon. And even though it's not direct, it has nothing to do with the band structure in our simple model. The band edge is way over there in K-space. This type of simple model for the dispersion is used to take into account non-parabolicity effects. Okay, and the last thing that we can get some insight out of this model for is tunneling. So we derived this two-band model. We then looked at what happens for small k near the band edge and how you derive this thing that people commonly use and just sort of write it down. And in the textbooks, you'll commonly see that they'll say something about, coming from a k dot p model, you can derive this expression. Well, we derived it from a tight binding, but later in the course, you'll see it's all, you can go back and forth between the two. So for low energy near the band edge, if you're only worried about one band, you can make some corrections using this. You can find alphas in textbooks or our journal articles, databases. But some more insight we can get from our two-band model is to look at tunneling, what it does for the tunneling problem. And let's see. So this is something I talked about in the very first lecture. One of the motivations why you need to go beyond simple parabolic model. So this is my favorite set of materials because the parabolic model just utterly fails most of the time when you're doing indium arsenide. And then if you want to do a tunnel from indium arsenide through a barrier made of aluminum antimonide, your parabolic model will utterly fail you. And this is the thickness of your barrier. And you're coming in here, your electron wave is being injected at that energy. So, right, in this picture, this is your traditional band diagram where this is energy. This would now be position. That would be your conduction band edge, X instead of K. E versus position, right? Your conduction band edge of this heterostructure. And so we'll call the top of the barrier EB for the energy of the top of the barrier. And you're tunneling through at energy E, and this distance is going to determine how well you tunnel, this energy difference, EB minus E. I mean, it sort of makes sense, right? If you're very close to the top of the barrier, you ought to tunnel through pretty easily. If you see a really tall barrier, you're not going to go through so easily. And what determines your tunneling in a simple WKB type expression is your tunneling probability would be proportional to E to the negative 2 kappa D. And in the effective mass model, which is your parabolic model, this kappa you just get from the dispersion, where it's going to be square root 2 m star EB minus E over h bar. So this is all we did for our parabolic. If you remember, for our parabolic model, K is square root 2 m star E over h bar. So that's our relationship between E and K in the parabolic model. And so this is for, if we just consider this energy up here, for K in this material, this would be the relation. If I start with, E, set my energy 0 to there, and I have a plane wave propagating up here, this would be the relationship between the K and the E. Down below the 0, down in these energies in this material, in the aluminum antimonide, I just sort of turn it upside down. My K becomes I kappa if we go through the whole thing, and I just look at the energy sort of going down from the top of the barrier into the band gap of the aluminum antimonide. And I think we mentioned this. You can get this relationship just by letting K go to, I guess, I kappa. Letting K become imaginary in the barrier. At any rate, this is the K that would govern the tunneling in our effective mass model. I guess I actually derived that. How much time do we have? Oh, as usual, we don't have any time. Whenever I ask that question, we have like 1 minute left. Okay, so I guess we'll derive that next time, and then show what happens when we do compare the two models for tunneling, and then we'll finally start doing a real crystal, silicon.